In Objective 3, in this lesson about inverse matrices, we're going to solve a system of equations by using an inverse matrix. Okay, and we've seen this picture before. This is that picture with that girl with the lovely shoes and her little foot tattoo. She's going down one side of maybe a mountain ski lift, and if she wanted to undo that, do the inverse, all she had to do is come up the other side, right? Concept of inverses, undoing what you just did. Okay. So we're going to use an inverse matrix to solve this linear system. So in another lesson, we learned how to write this as a matrix equation. It goes like this. First, I need the coefficient matrix. So the coefficient matrix would be a 4 going straight across here on the first one, a 4, a 1, and on the next equation, a 3 and a 5. This would be multiplied times just a 2 by 1 matrix, the x and the y, the two variables that we have, x and y. And this should be equal to the set of constants out here, the solutions, a 10, negative 1. So remember when we talked about maybe Kramer's rule, if I take the matrix multiplication on the left-hand side, the 4, 1, multiply it times x, y, I will get 10. That's the first equation in the system, right? Okay, so in order to solve this for x, y, our answers, we need to get rid of this matrix. I get rid of that matrix, the coefficient matrix, by multiplying by the inverse. So that's what I'm going to do. So my answers, x, y, is equal to the inverse of my coefficient matrix, 4, 1, 3, 5, inverse, times the 10, negative 1. 10, negative 1. Okay? So, whenever I go to find the inverse of that coefficient matrix, I, of course, need to first find the determinant. So 1 over 4 times 5, I got 20, minus, and then 3 times 1, 3. Well, that's going to be fun. 1 over 17 is what that will be. And now scramble up the numbers in that inverse. The 5 goes there, the 4 goes here, those two switch. And then negative 1, negative 3, those switch signs. Now I'm going to multiply that times a 10, negative 1. Okay. So I'm going to take a 2 by 2 and multiply it by a 2 by 1. My answer should be a 2 by 1. Okay. So let's continue this. 1 over 17. I'm going to leave it there. It's a fraction, and I don't want to have to multiply that through this inverse yet until the very, very end. Okay. And now let's do the matrix multiplication. I'm going to multiply the first row times that column, 10, negative 1. So 5 times 10 is 50, minus or plus 1. Plus 1, negative 1 times 1, negative 1. Okay, there is the first row whenever I simplify that. And now let's move on to the second row times that column. I'd have negative 3 times 10, so negative 30. Plus 4 times negative 1, negative 4. Okay, let's keep simplifying here. 1 over 17. And up top I have a 51. On the bottom I have a negative 34. Okay, so let's now just divide those two numbers by 17. So 17 goes into 51 3 times, into negative 34 negative 2 times. So answer to my system of equations, the original system of equations, is 3, negative 2. So what we just did is we came up with another method to solve a system of linear equations. This time, no substitution, no elimination, and even no Kramer's rule. Another one using inverse matrices. So if you needed something to write down for steps, step number 1, you're going to first write your system of equations as a matrix equation. Matrix A is the coefficient matrix. X is what you're looking for. If it's a 2 by 2 system, it's a column X, Y. Okay? And then equals B, those are the constants that you're equal to. You might think of those as the answers, right? Okay, so step 2 then is you're going to find the inverse of matrix A. Find the inverse of matrix A so I can get rid of it on the left side of the equation over here. Okay, and then finally step 4, multiply the left side, both left sides, by the inverse of A. So your solution is x is equal to the inverse of A, that's the coefficient matrix, times B, which is the constant matrix. Okay, so let me reiterate this pro tip about the inverse matrix and having to deal with the determinant, especially when the determinant turns out to be a fraction that we don't want to distribute until the very, very end. Okay, so this is the same system of equations that we just solved on that example. So in order to solve that, again, I'm going to multiply the left-hand side by the inverse, right? So it looks like that. Okay, whenever I find the inverse of that matrix, that 4, 1, 3, 5, the coefficient matrix, I get the determinant 17, which means that I would multiply everything on the inside by 1 over 17. I don't want to do that at this point because it's going to create a whole bunch of fractions that I'll have to multiply times the other matrix, 10, negative 1. So I'm going to call this thing in green here the sub-inverse. Okay? So go ahead and multiply the sub-inverse by the 10, negative 1 before you deal with that scalar 1 over 17. Okay? So do that multiplication first, then deal with the 1 divided by the determinant as a scalar. So then go ahead and distribute it through and you have your 3, negative 2 as your answer. Okay? So here are two of them that I want you to try. Solve each of these systems of equations using an inverse matrix. Get a little bit of practice right there. And then we're going to move on to 3x3s. Okay. All right, so here we go with some answers. The first one, whenever you go to solve it, you get 1, 2. And the second one, something strange happens, and the ultimate answer is either one of these, infinitely many solutions or no solution. So let's look at both of these in more detail here. So for the first one, writing the equations, the system of equations in a matrix equation. So coefficient matrix out front times the variables x, y is equal to negative 5, 8. Okay, and then in order to get rid of the coefficient matrix, we're going to multiply by the inverse, which is what's right there. In order to multiply by the inverse, I've got to find the inverse, which is 1 over the determinant. Turns out to be 1 over 2. And then the little sub-inverse is formed by switching the elements along the main diagonal, switching the signs on the ones on the minor diagonal, and then multiplying that times negative 5, 8. And just like I've talked about before, we're going to leave that 1/2 out front until I've done the matrix multiplication. Okay, so then your final answer does turn out to be 1, 2. Okay. And then finally, number 2. Do the same exact thing. Make yourself a matrix equation, coefficient matrix right out front, multiply by the inverse of that coefficient matrix. In order to find the inverse of that coefficient matrix, whoops, that should have, whoops, right here, should have a little negative 1 there. Okay. In order to find that inverse, I need to divide everything by the determinants. However, whenever I find the determinant, it turns out to be 0. 1 divided by 0 is undefined, which means I can't do it this way. Think back to the last lesson on determinants. What a determinant determines is whether or not you have a unique solution. You do not have a unique solution whenever the determinant is 0. That means that the slopes are the same. Could be the same equation, or it could be two different equations that are parallel to each other, different y-intercepts. So your conclusion is either infinitely many solutions or no solution. Now further from that, what we could do is look back at the original set of equations. Just take a look at them. The bottom equation is the same thing as the top equation, just multiplied by 3. If you multiply everything by 3, you get the exact same thing as the bottom equation, which means that they're the same equation and it's infinitely many solutions and not no solution. Okay? Alright, so that concludes solving a system of equations in 2 variables using an inverse matrix. Now we're going to move on to 3.